There we go, we're recording again. All right, before we get into this today, you can already see that the layout has changed, and I have retroactively changed the layout on all of these slides, not on the slides shown in the recordings, of course. That's because this study group is no longer affiliated with Aarhus University. I still am, but after some things which I would rather not get into for fear of spreading some bad vibes. This study group is no longer affiliated with the University of Aarhus. I am not getting paid for it. I never have. And I am now doing this completely on my own time just because I'm having fun doing this. So just a quick explanation of what's happening here with the layout, and everything else will continue just as you were used to. Everything else will be the exact same. All right, that out of the way. Today we're talking about generalized linear models. Whereas the chapter and the lecture made this all about maximum entropy, I think what we really are interested in ourselves is the generalized linear model component to this instead of the entropy talk, even though it's important, of course. And so by going into this, I actually need to click into PowerPoint to get this rolling. First, I'll quickly give a quick recap of maximum entropy, then move this all over to the actually important things for us with generalized linear models. So if you've read the chapter, which I hope you have today, you will have noticed, as have I, that there was about 80% maximum entropy and then 20% generalized linear models. You'll have the inverse of that in this presentation today. So maximum entropy. What is it aside from the butt of a joke that everyone with a high school physics education makes? Maximum entropy all comes down to how a certain probability function looks like. So entropy itself, not even maximum, just entropy, is an inverse proxy of the probability centralization or density in a distribution. What I mean by that is the more peaked a density distribution is, probability density distribution that is, the less entropy it has. The more flat it is, the more entropy it shows. So the most entropinous, the distribution with the most entropy would be a completely uniform distribution that stretches from negative infinity to positive infinity because it's all on the exact same level and it's completely flat. Now, entropy also, when we go back to the counting examples which we worked on in our earlier seminars, entropy is also a proxy of the number of ways in which a distribution can arise. So for example, if we think back to the drawing of different marbles from, I think, our second session, you may recall that we looked for combinations which would produce two blue marbles and one white marble to be drawn from a bag in 3 draws. And to produce that, you have a number of different ways in which you can get to the end result, because with this end result, we're not interested in the specific order, just the actual outcome. Same thing you can see on the right-hand side, where thought experiment-wise, you would toss 100 pebbles. No, in this example on the right-hand side, it's just 10, where you would just randomly toss 10 pebbles into 5 buckets completely at random, and then see how many ways you could have tossed each individual pebble to then come to a distribution of, in the first example, 2 pebbles in bucket 2, 3 pebbles in bucket, 6 pebbles in bucket 3, and 2 pebbles in bucket 4. And that works out to be 1,260 ways with which you could have thrown your individual pebbles, because only the outcome matters to us, but how we get to the outcome matters for the probability. So the distribution with the largest entropy, as you can see, our probability distribution getting smaller and smaller, or flatter and flatter, and our number of ways in which we can obtain said distribution increases a lot in these plots. You can see that the distribution with the largest entropy, meaning the most number of ways in which it can arise, is the one that is consistent with the stated assumptions and the flattest. So our stated assumption being, we've got 10 pebbles, we do not care about the order in which they fall into the buckets, just where they end up landing. Now, the relevance for Bayesian approaches comes immediately with this link to Bayes is basically just counting, just in a very fancy and black magic kind of way. And this entropy lens, which we can view our different approaches through, helps us to understand priors of parameters, for example. It helps us to understand the likelihood of our data by looking at the entropy of the distributions in both our priors and the likelihood of the data that we assume. It also reproduces Bayesian updating with something called minimum cross entropy, where you try to find the best update to your previous distribution by keeping as much entropy in your remaining distribution. So when going from your prior with a certain entropy to your posterior with a certain entropy, you would want there to be as little change as possible with minimum cross entropy. And that's the updating step. Does that make sense? Coolio. So without knowing anything, we would like to bet on the flattest distribution, which comes all the way back to uninformative priors, which are just completely flat. But usually we know enough that we don't want to bet on a completely flat distribution because we actually have some understanding or intuition about what we want to look at. So when picking entropy distributions for certain outcomes, and we'll get to that in a bit more detail when I talk about generalized linear models today, when we have certain constraints or assumptions about our outcomes, certain maximum entropy or max end distributions arise. So if we have real value distributions or real value outcomes in intervals, then we would, or in one big interval, sorry, we would like to use a uniform distribution because that one's completely flat. Now, if we have real values with a finite variance, then we would like to use a Gaussian distribution because that gives us the distribution defined simply just by the mean and the variance, which is finite and symmetric in its application. Whereas flipping back to the first one with real value in an interval, the variance is not so much of interest to us as is us sticking to the interval. So for example, we would like to look at how many packets of soup an individual buys when a hurricane is approaching, and every customer is limited to 10 at maximum. We would have an interval with real values between 0 and 10. Because you could go into the store and buy 0 soup packets, or you could go into the store and buy 10 soup packets, making use of that maximum that the store allows for, but you can only take integers in between. You could also take something else where the real value comes in with decimal places, and then we would probably look at grams of rice that someone buys in case of a disaster approaching. This is where we would go for uniform rather than finite variance, I say, if there are certain boundaries which we know we have to adhere to with our outcome. If we look at binary events with a fixed probability, so that's a fixed probability of actually buying a soup pack when a hurricane is approaching, then we would look at a binomial distribution. And if we look at non-negative real values which have a mean, we would like to use an exponential function. And more on that in just a second, don't worry. Just flipping us back to the counting example from, I think it was the second seminar. When we count the paths that lead to a certain outcome, then we actually do produce the flattest distribution that is lying within the constraints that we have stated prior. So by drawing this garden of forking data, as McElraith calls it, by simply just following each path, which gives us the desired outcome, we can identify the path or the path combinations that give us the most. The path combinations, so taking a step back because I can feel myself sounding a bit like a conspiracy theorist here. When looking at this diagram here, and I know this doesn't help with me sounding like a conspiracy theorist pointing to a diagram like this. It will all make sense in a second now. We have a certain outcome. Our outcome is blue, white, blue, or 2 blue, 1 white. Now, our conjecture in this case is that we assume our bag holds 1 blue marble and 3 white marbles. If we now tally up all of the different draws with which we get to our outcome, 2 blue marbles, 1 white marble, given the constraint of our data looking like what you can see up there, so 1/4 blue marble, 3/4 white marble, what we end up with is the flattest possible distribution by having counted all of the ways for this conjecture. If we were to count all of the different ways in which we could get 2 blue marbles, 1 white marble from a bag with 2 blue marbles and 2 white marbles instead of 1 to 3, we would have a flatter distribution still, because now there are more ways that we would count to get to the outcome. And we can do that for all of our different conjectures to get to our output, which is constraining the paths that we count. And then we can just simply take the conjecture that had the most counts associated with them, because that gives us the flattest distribution. And I see some nods, so I'm going to move along. That's actually all I wanted to mention about maximum entropy. I find it a bit abstract, and you could probably tell I had a bit of problems explaining it because I feel as though I have not quite understood it fully yet, because usually I like to learn most of these concepts through the exercises at each chapter. So while I was happy that there were no exercises this week for time savings, I do not feel like I have the most solid of grasps on this topic so far. So like always, please step in at any point in time and either make me break through the thin ice I'm skating on right now, but then also try and help pull me out in terms of explaining these things. So generalized linear models. I have a question,
Eric. Just I don't want us to get hung up on this because you did an awesome job with entropy. But so are we supposed to take that as an underlying feature of these models that we run? Is that no matter what, we get a distribution with maximum entropy, or is that an assumption? Is that something inherent and something we can just like take de facto, or is it an assumption that we should have? Like, is there a possible way to come out with this with more entropy?
That's an interesting question. I would absolutely argue that we should not assume our models to have maximum entropy, because from how I heard your question, and please do correct me if I misheard that, it sounded a bit as though you were using entropy as a stand-in for quality of the model.
I was just thinking of it in terms of, it was really well put that it's just a number of ways, right?
Okay, so I'm going to try something, and you tell me if that comes across. Given all of our constraints to our models, and our constraints being the data, our priors, and the likelihood distribution which we assume for our outcome, our Bayesian models will always end up with a maximum entropy distribution.
And that'll always happen.
Yes. Now, does that mean that maximum entropy distribution is representative of what's actually happening in the real world? Of course not.
Okay.
It could be, but it doesn't have to be.
Gotcha.
So we want to play around with our model constraints as much as possible to get to the highest entropy distribution that we can get to.
That makes sense.
Cool. All right, generalized linear models. This is where we now get into, and thank you, by the way, for stepping in here and asking that question. With generalized linear models, we now get into what do we actually do with maximum entropy. So the strategy behind generalized linear models, because what they allow us to do is model multivariate relationships and nonlinear responses, just like they do in frequentist analysis. Because quite frankly, there's not that big a difference between Bayes and frequentism. It's just a few minor things here and there. So much of what these methods are used for is the same in both disciplines. Just the way we initialize them is different. So in the Bayes way, what we have to do is we have to select an outcome distribution according to maximum entropy principles. We have to select model parameters, and we then have to link these to a linear model. What I mean by this will become clear in a second, I hope. And I wish that someone had explained this as well as the book has when I was taught statistics, because links never really made a lot of sense to me, and they are starting to make a lot of sense now. And once we've chosen both of these, the outcome distribution as well as the link functions, we're then ready to compute our posterior. So first, let's start with outcome distributions. How do we choose them? A lot of people will choose them according to the histogram of the distribution of the outcome variable, which bad choice, but I'm sure we all know that by now. So I think what's more important for us is to highlight what kind of families of these functions are actually out there for us to work with. And most all of these, which we'll end up using in the book, at least from what was written, and what I can see for our real world examples, are in the exponential family. So we always, almost always, start with an exponential type outcome distribution. And what the exponential distribution by itself just tells us is that there's the same proportional rate of change across the entire distribution. That's all that the exponential does. Now, when we want to move to count events, we would probably like to move to either a binomial distribution or to a Poisson distribution. Now, a binomial distribution has counts with a certain ever stable probability of receiving one over the other. So we have two outcomes, and the outcome probability of outcome A is always for every single repetition of our trial the same, whereas the outcome probability for B is always 1 minus the outcome for A, so the probability for A. So binomial distributions we would use if the expected value of these counts is high. Now, if we have many trials but a low probability, we would move to a Poisson distribution where the expected value is low. Because a Poisson distribution, instead of being driven by n, the number of what we observe, and p, a constant probability to observe n however many times, the Poisson distribution is simply just driven by lambda. And I quickly have to step into my notes here for this, because I think I made a better point in my notes about this. All of my notes are available in our drive as well, by the way. So the Poisson distribution is constrained to be anything between 0 and positive infinite, and is described by lambda, which is the rate of events occurring, instead of the probability of something happening. So if we now go back to our exponential core function, we could be interested in a sum of events or a sum of different values to be explored, in which case we would usually go for a gamma distribution, which a gamma distribution is also constrained to be between 0 and positive infinite. It can have a peak above 0, and the shape is described by two parameters, which is lambda and k. So what I mean shape above, peak above 0, you could reasonably say, but you just said it's constrained between 0 and positive infinite. What I mean by that is simply just in relation to its grandfather, the exponential distribution, which you can see here in the middle. The gamma distribution can have a peak anywhere, including but not limited to the first point that we draw in this distribution. I'm really not using my words well today, I'm sorry about that. But you can see how the exponential function just slopes down across its entire range. The gamma distribution does not have that constraint with it. It can go up and then down again. It only does that once, but it doesn't have to have its ultimate peak at the beginning of its distribution. Now, if we then move from gamma to a normal distribution, which we are already quite used to and which unfortunately has cemented itself as the standard starting point for most people, myself included, by the way, we would like to look at gamma distributions with a large mean. Because at that point, this hump that I was just talking about shifts so far to the right that the variance becomes very interesting to look at and usually also symmetric. And in that case, a normal distribution makes a hell of a lot of sense as our outcome distribution. Now, I wish I had a better flowchart-like visualization of when to choose which outcome distribution, but I don't know that myself yet, and I really hope that the next few chapters and corresponding exercises will make that a bit more clear to all of us. And if any one of you has a better understanding of when to use, or just a different one, not even a better one, just a different one, a different understanding of how to choose outcome distributions, please do speak up.
I don't have a better explanation, but I have a question regarding Poisson and binomial again. So you said that Poisson is like the rate, the lambda is sort of the rate of an outcome of the occurrence of a certain outcome. So isn't the rate of an outcome similar to like the probability of an outcome? So what's the difference between the lambda and the p from the binomial?
It's a good point. I think there's certainly a parallel here between these two, but our binomial distribution is always additionally informed by how many tries per observation do we have. So I think p and lambda correspond with one another. Just one function or one distribution is additionally bound by however many tries we have, the n.
Also, I mean, I'm not sure I'm going to say this correctly, but for example, the binomial, you have a binary outcome. And then this binary outcome, the possibilities that you have may happen with a certain probability, right? So you have a coin that can be a fair coin or not, and then you toss it and you have head of tails. Instead, the Poisson is, so it's like the frequency of an event, but it's not really a binary event. It's like you're at the post office and you ask yourself, how many people are in line with this, at this desk, at this, what's the name? At this, with this person at any given time, and you're gonna have 5 people in line, then 3 people in line, then nobody, then, and so on. So it's a little bit different outcome and situation, right?
I think what Bernd and I are getting stuck on right now, and please feel free to tell me I'm completely misinterpreting your thought process, Bernd. I feel as though you could just break this thought example of people standing in line down to the individual person and then saying, what's the probability of each individual person queuing up? And that's a binary outcome again, because either you queue up or you don't. And then you're back to a binary outcome with a event rate, which would be the average probability of queuing up for each individual person.
I mean, that makes sense, but I think in a Poisson, you're interested, the outcome you're interested in is how many people are in line, not so much what's the probability of a single person of being in line or not, if that makes sense. But usually when we apply the Poisson is that because we have counts, right? And not so much a binary outcome. So I think maybe, I mean, that depends on the question you're asking and the answer you're looking for.
To be fair, with this specific thought example, what I just said would be really difficult to study, because while you can count the people who queued up, you can definitely not count the people who did not queue up, because they will never show up in your data. Because if you only have access to the queues, you cannot make this a binomial, because you don't know the people outside the queues.
And regarding this people example, I think for binomial you said it's important that it's always p, and the opposite is 1 minus p, and this has to be constant.
Mm-hmm.
So regarding for the people example, I think maybe there are more patient people which more likely queue up than unpatient people, which just come back later. So this has like different peaks per person. Huh?
He says with 2 Englishmen in the call.
Don't get it.
Because they just queue up way more than other people. We had a Christmas party in Norway where one of our English colleagues was giving the thanks for the dinner speech, and he listed off all of the great things about Norway in comparison to Great Britain, and then he came to queuing etiquette, and that's where he laid into the Norwegians really hard.
I'm not a queue person.
No, I was just about to say that the Germans aren't much better. Have you ever seen a school bus pull up in Germany? There's no line.
Yeah.
It's just a mosh pit.
True.
I was going to say as well, I think for me, with the binomial, I think what we've sort of been alluding to is the fact that this fixed number of trials is really important. The fact that we do specify n as a, that, whereas we just have this average rate with Poisson. And I don't know whether there's there's quite nice parallels that can be drawn by the fact that the mean of the binomial is NP, whereas the mean of the Poisson is just this rate lambda, which also happens to be its variance.
Yeah. Yeah, that's another good point. I really hope we'll get a better understanding of this over the next few chapters, I hope. That being said, not next week, because that's where we have an input speaker who I'm really excited for. All right, let's walk a bit more through each individual step that I mentioned earlier about how to do generalized linear models. So as you remember, the first one was outcome distribution. I just talked about a few different outcome distributions. And first step we have to take is pick one. Here's a few examples. When we want to study, for example, counts, we would like to look at Poisson distributions or binomial distributions, depending on the setup of our study, I'd assume. So if we actually have a fixed trial number, then we would probably like to look at a binomial distribution. If we don't have a fixed trial number, then a Poisson distribution, to my mind, would be much, much more useful. When we have distances or durations, we would probably like to look at exponential functions or gamma functions. So for example, with dispersal events, we would probably like to look at a gamma distribution because we could argue that dispersal will not happen. Let's think about a tree, for example, just evolutionarily thinking. If a tree drops its seeds right next to its stem, that will just kill all of the seeds off because they won't be able to compete with the already grown tree. Now, if they drop away from the tree in, I don't know, 20 to 50 meter radius, they'll probably flourish because they won't be inhibited by their actual parent tree, but they will also still definitely be, unless there's a cliff or an active volcano right next door, still be in very livable conditions, which were capable of actually hosting the parent tree to begin with. So that's where our probability of observed distribution should then converge on some, I don't know if you can see my mouse, but I'm pointing at that hump up there, where our observed highest probability of distribution in terms of distance will be at a certain distance relatively close to the parent tree, but not too close, and then decrease as you get further and further away. One, because seeds just can't spread that far unless we talk about dispersal via birds, for example, but even they have a certain range limit. And conditions just might get worse and worse for the seed itself. So that's where the gamma distribution might be interesting. Now, if you look at time events, we could, for example, take traveling of sound. Let's say someone snips their fingers. Now, actually, no, we could just go with Zoom, the call we're right now on, because anyone who's in the same room with me, so doesn't have as much of a separation as, for example, Serena or Rosen have, who are very distantly located from us, there will be much less lag. So the lag, meaning, let's say that corresponds with quality of our interaction. The quality of this interaction due to missing lag will be highest to someone who's sitting ear to mouth with me, and highest for someone who's sitting all around the world. And that's why we would like to look at an exponential function. I know that was a bit of a contrived example that sounded very, very unpleasant at some point there, but I still hope that makes sense. So other distributions for monsters, as McElroy calls it, and there will be a chapter called monsters and mixtures, I feel like. So I'm not going to go into those monsters or mixtures because I feel as though that will come up later. Again, when choosing an outcome distribution, do not eyeball the outcome distribution from the histogram of the observed outcomes. Just throwing that in there. I love the term histomancy. I really do, because it gives me D&D vibes, but I didn't want to put it on here, because I'm already basically stealing half of the slides here with just me copying them in. Second step of getting to a generalized linear model is identifying the link function. I mentioned earlier that I wish someone would have explained these better to me when I learned about these concepts. So now I'm hoping to make a better point of explaining these myself. So when we model the actual parameters in our generalized linear model, what does that come down to? In the notation of our model, we always have a certain likelihood to our actual outcome. That likelihood is our outcome distribution. So right here in the top example, we use a normal distribution as our outcome distribution. In the lower, we use a binomial distribution as our outcome distribution. So this is where the outcome distributions come in. Now, unfortunately, when we choose certain outcome distributions, their scale does not link up with what an underlying linear model would produce. So an underlying linear model might be very, very bad to use the parameter estimates of when we actually want to look at our outcome through a certain outcome distribution. So in binomial, for example, we would be interested in probabilities of, let's say, survival, for example. And a linear model has absolutely no problem at all predicting survival probabilities way above 1 and way below 0, which doesn't make any sense in terms of us wanting to explain something. And this is where we have to link the linear model space to the likelihood space, the outcome distribution space. So on the right-hand side, you can see how there's still this linear portion to the model, but because of our link function, the ends now curve slightly back. So they do not go beyond 0 and 1 in this example. We will get to this with more of an example in a second here, but Bernd.
I have a quick question again, sorry. So these, if you can go one step perfectly, so these outcome distribution, which is here normal or binomial, that's the thing we choose based on our knowledge or intuition. We choose like to have the maximum entropy. That's where the topic started, or that's where the point actually meets in.
Yes.
Okay. Yes, it's perfectly fine for me. Excellent.
Cool. No, great. Thank you for asking that question of clarification. Really good. Please never feel like you have to say sorry for asking a question, because after all, we're still a study group. And I'm always happy when I actually get to interact with you guys, because I feel this has morphed more into a me talking to you guys series. So every time someone unmutes themselves, I get giddy inside. Now that we've got our link function, we are ready to compute the posterior. And this is where MCMC comes in, because the search for our posterior is harder given all of the different parameters and functions and what have yous that we just implemented. The links matter, the interpretation's harder. Quadratic approximation may do well, but doesn't work always, especially when we don't have a certain hump in our distribution, a distinct one that it can converge onto. So it's safer to rely on Markov chain Monte Carlo when we actually compute the posterior. What also stems from this is that variables interact with one another in what they mean in terms of slopiness for their parameters as a consequence of compressing scales. So compressing scales happens through link functions and choosing different likelihoods. And once we enforce these different constraints on our data, even without specifying an interaction effect in our model, we may observe interactions between variables and their parameter estimates in certain regions of where they're plotted. An example for that, because it took me way longer than I care to admit to wrap my head around that tiny sentence that McElrath said in his lecture. So basically what is meant by this, from what I have gathered, is that there are floor and ceiling effects. And there may not be just floor and ceiling effects, there may also be effects of flattening out somewhere in the middle and then sharply rising again, or falling down. So basically, what you can see here is the probability of survival of a lizard, given temperature. Now, if we were to model the effect of temperature and diet or food availability of that lizard and want to get survival as the outcome, so a probability of survival, then at a certain point, no matter, even though food will probably have a beneficial impact on the survival likelihood or survival probability of our lizard, at a certain point, it gets so cold that all of our lizards just die and food will not benefit them anymore. So even though we haven't specified an interaction effect between these two variables in our model, just by virtue of what's happening in the data and with our constrained functions, we will get to these floor and ceiling effects, at which one parameter or multiple may have such big an impact that the impact of other variables just drops out completely. This also brings us to finding the right parameter or finding the right slope, which is tricky for anything beyond basic linear regression. And that's as much as I can tell right now, because again, I want to solve exercises related to this. Otherwise, I probably won't get it. As an example, which I'll just quickly walk you guys through, I'm actually taking longer than I expected, which also good because I can feel myself understanding this a tiny bit better just talking about it myself. As an example, we'll just consider binomial distributions here. So this is a hypothetical binomial where we could just look at, for example, water count on the globe toss example, or blue marbles in our forking garden of data, or drawing of cards, which we talked about in our second session. So we have counts of a specific event with n possibilities. So n trials which we repeat until we conclude how often something occurred. We have a constant expected value, and our maximum entropy distribution then turns out to be a binomial one, where our outcome y is the count of our successes, blue marbles, black face cards, not the dog whistle races and kind, but, you know, spades and crosses, and water on the globe, for example. N is the number of trials, and P is the probability of success. Now, if we just count this up on the right-hand side, Poisson-wise, we would end up with something like this, for 4 being the most common one out of 10. When we talk about our constant expected value, what we mean is the mean. So that is n times p. That's the expected mean value. The variance of that outcome is then just n times p times 1 divided by p. 1 subtract p. Once we have identified our outcome distribution, which is just what we've done, we have settled on a binomial given the constraints of our data, which was mean expected outcome, fixed number of trials, we count successes. We now have to link whatever is happening in the linear model portion of our generalized linear model to this outcome space, with the outcome space being binomial distribution. And what we use for this one is a logit link. A logit link simply just takes the log odds of our linear model estimation of the parameter. So on the left-hand side, you can see that in log odds space, our linear model works perfectly. Straight line, everything's great. Now, if we transfer a log odds space to a probability space, we get this nicely curved relationship, which is what we're after, which gives us this logistic regression line, which we are used to from GLMs run in R on frequentist packages, which I think in R is even base R. You don't even need a package for that. So on the right-hand side, you can see a bit more of a calculation of this. So you can see how here we have our outcome. We have our outcome distribution, which is binomial, given the two constraints that we have, n and pi. We then take the logit of the pi, which we model or infer using our linear regression. And that gets plugged back into our binomial likelihood distribution to then form our outcome, where the outcome is going to be the probability that we want to look at. And thankfully, we, from my understanding, don't have to look too much into how to obtain these different links and which ones make sense, because mathematicians have already done all of the heavy lifting for us. Because if we then end up plotting log odds versus probability in the same space instead of left to right like we did here, we can immediately see how a certain value in log odds space relates to a certain value in probability space, where your linear model is free to go wherever it wants in log odds space, which you can see over here and over here, because it has that linear, that linear line, Eric, which can go wherever it wants beyond any bounds which may seem sensible. Because of that logit link function in probability space, anything that goes beyond log odds of -4 or 4 would basically always correspond to a probability of never occurring or always occurring. And that's the beauty of using these links, because we transform what our linear model tells us into our desired outcome distribution. And so the logit link is just one out of many which you could use for binomial distributions. Others include probit or log-log, but in all truth, I don't know enough about these yet to make any statement of when to use which, and I hope that'll become a bit more apparent over the next few sessions. And that was my rambly summary of what was in this chapter so far. Yet again, I hope, and I'm pretty sure with how things have gone so far, that this is just a temporary confusion that I'm facing, and I'd be interested in whether you're facing a bit of confusion here as well, which hopefully will be cleared up over the next few coming weeks and seminars. Did anyone feel like they really got down with this topic?
I'll put my hand up and say I've never really understood the link thing. I see a chapter on GLMs in a chapter, I'm like, I'll know how to code it, but visualizing what it actually does to a point or generating a curve is really tough for me. I wanted to ask you guys a question. When you talk about GLMs in like a frequentist manner, you intend to talk about information criteria as well. And this chapter started with the entropy angle. So when we're picking our link functions, should we use those entropy measures as like an information criteria? Should we use like number of ways as like the way to go, or should we come in with a desired link function and then have a way to justify what's correct to do?
Yeah, that was a really good point about using information criteria with these kinds of models in the book. And I'm just going to read verbatim from my notes here, if you don't mind. Yeah. using information criteria, WAIC, AIC, BIC, etc., to compare models with different likelihood specifications is a fallacy, since the outcome distributions or likelihoods come about differently and their respective constants do not drop out when we try to compare the different outcomes. So if you have GLMs which have different outcome distributions associated with them, you would not want to compare these different outcome distribution GLMs with one another using information criteria.
Mm-hmm.
And you would much rather want to do actual cross-validation, for example.
Yeah, that sounds right.
That being said, from what I understood, sorry, Ben, from what I understood, when you have different GLMs, which are all built with the same outcome distribution, just different parameters added to them, for example, you could still use AIC and WAIC, because now all of the different outcome distributions subtract out or divide out between the different models.
That makes sense. Yeah. That makes sense. Thanks. I completely forgot that. I'm pretty sure I heard someone say that in a lecture like a year ago, like you can't do that with different link functions. And it just completely escaped me. We were talking about entropy. Thanks. Yeah, that makes sense.
So I got confused, like the question from Sam was about the link function. So if you choose like logit or log or whatsoever. Yeah. And the answer of Eric was regarding the outcome distribution. So if you choose like normal or binomial or exponential, isn't this like two pairs of shoes? I get the point that we can't use the information criteria because like one model is fitted on like the idea of being like Gaussian and the other one is fitted on like being exponential. But what's the point regarding the link function we choose?
So where I came from with my answer was whichever outcome distribution you pick will often drive you to picking a certain link function. So I think in answering the questions of how can I compare models with different link functions, we often have to take the step of, so which link function is it you're taking? Okay, you're looking at a logit link and a whatever link. One points to a binomial distribution, one points to a gamma distribution, for example. Then we can't compare these two because they're looking at different spaces.
But if we have the same distribution,
if we had a binomial distribution and we used a logit link and a probit link,
for example, yeah.
I don't know.
Okay, but
intuition would tell me no, you can't. But I do not have a good reason. That's just my gut feeling.
Yeah, I never worked with such kind of models or these link functions, so I really have no idea. But I was just like, for me, it's also new that like these links functions are then linked, or like you have specific link functions hiding or towards like a given distribution. So I thought you can choose like whatever link function you want for whatever distribution you have.
Right. That's unfortunately a no.
Okay, good.
Because the logit function needs to match with the desired outcome distribution. Otherwise, your link function will mangle the parameter estimate in a certain way, but that parameter estimate might not necessarily coincide with your desired outcome space.
Yeah. So how do we justify it? So let's say we've got multiple link functions that we can use for a similar outcome distribution. Do we just go, hi, we discussed about it, and then we coded it, and then it works? Pretty graph, run away, don't discuss now. Or do we just, or is there like a specific statistical argument that we need to make, like is often said for like frequentist stuff, where there's like a specific way you've got to describe stuff? Is there a specific way we could go from prior to link to being?
So I would argue, having knowledge of what we want to model, we would definitely have all of the constraints that inform which outcome distribution we're interested in. So outcome distribution, we should always be able to get to without much discussion of which one is most applicable. Then I would hope that a lot of mathematicians have already done the groundwork of telling us which link functions are potential candidates for our given outcome distribution, which we've landed on, and then settling on the right outcome distribution, on the right link function would, for me, come down to either seeing if someone else has already established which one's the right one, or just doing them all and then doing cross-validation and seeing which one performs best. So a sensitivity analysis.
Fair.
But that's just because I like to hide away from actual manuscript writing by doing unnecessary coding.
No, all your coding's very necessary. I love your coding. It's awesome. No, that's really cool. It was just something I was thinking about because there's like a cool connection to make between entropy, which was basically exactly as it's taught in a chemistry classroom, and then connecting that to the whole Bayesian and then like GLMs. I was like really interested. And the link function has always eluded me visually.
I hope we'll get to a point where we're able to extract the entropy measure from a model.
That would be ideal, because then that would kind of solve all of our issues here, because then we wouldn't be confounded by link functions.
Well, to a certain extent, you can at least get this minimum cross entropy that would just be the difference between shape of your prior and your posterior.
Yeah.
But that's just like comparing models with AIC, for example, where the absolute number doesn't tell you much, but the relative magnitudes tell you a lot. Unless your AIC is 0, in which case it tells you a lot.
Yeah, that makes sense.
Actually, maybe the our documentation of the GLMs might help with families and links. I can just put the link here, which I found.
Thank you. You're saving the day, Anna.
There's some families where you can use the same link as far as I see and the arguments. Maybe this answers a bit with what Bernd was asking for. For example, I mean, logit is clearly kind of linked to binomial, but things like the link inverse can apparently be used for different families, as far as I see. What do you think?
Yeah.
Mm-hmm.
Oh, yeah.
There's many links I've never heard of, but many I will never use apparently, but.
Yeah, I saw a talk yesterday from someone in the States who's affiliated with our lab who uses a C log link.
Okay.
Which is something called complementary log. Ollie, if I'm remembering that correctly. Yeah, he's nodding his head. Yeah, it was like something that none of us had ever heard of. She had never heard of it before, but she knew a statistician in the department said, use this one, it works. And I'm like, fine, but why?
How to choose.
I think it's really cool though. Yeah, that's really cool.
Was that out of the Blonder lab?
Yeah, I need to post that in the Slack, but yeah, cool. It was cool. Had a lot to do with seed dispersal.
And they didn't use
it was actually quite similar to the example. It was quite similar, yeah, to the example you were talking about earlier, Eric, which is like the Jansen-Connell hypothesis of how seeds get dispersed and that sort of thing. Everything just seems related, you know. No, it's a fully established. It's one of the main hypotheses to explain like high species coexistence in a small patch of forest. Yeah.
Cool. Well, I'm looking forward to Sam posting that recording so I can watch it as well. Then.
Yeah, you reminded me how I have to do
this.
Yeah.
All right. I think we've filled an hour. I don't want to cut the discussion short. I'm just running out of things to discuss because I'm just eagerly waiting for the next few chapters and hoping to get a better understanding following those.
Actually, I have a general thing I wanted to ask all of you. Did any of you get into the IBS Bayesian species distribution modeling workshop?
Yes.
Okay, I didn't, but
Yeah.
if there's any material, if you would like to share.
I'll bump it over. I'll bump it over, don't worry about it. Yeah, I got that message just as I was about to shut my computer off.
Mhm.
And within 15 minutes, I had signed on.
Oh, perfect. I didn't.
Yeah. No, I think it's a bit strange that they have just 18 participants allowed.
Mhm.
But yeah,
Okay,
I'll
cool.
I'll share the material I'm recording with you.
Thanks.
Coolio. See
Or you upload
guys.
it on the file driver,
Sorry?
or you can upload it on the Bayes working thing file
I'd
server
prefer
whatsoever.
to do that privately because the link for the Bayes stuff is all open access, and I'm super happy sharing it person to person, but in the end it's not mine to share. So I'd like to keep that under wraps for a bit.
Eric, you're turning into Robin Hood, like stealing from the rich, giving it to everyone else. It's awesome.
Well, yeah, you just wait when I come over to Oxford later in the year and I bring a bow and an arrow.
Exactly.
All right, guys, thank you so much for this. It was a nice
Cheers,
session
Eric.
again, and I'm looking forward to next time.